Welcome. After wrapping up the Brouwer story, which was a story about the Kirchhoff Laplacian, a one-dimensional story, I wondered about the higher dimensional case. Now it's very, very interesting that we have kind of two different worlds. We have a fermionic world, which is well known in the continuum, Riemannian manifolds. We have higher dimensional form Laplacians, like one form Laplacians or two form Laplacians here in a two-dimensional situation. And then we have a connection story which doesn't exist in the continuum, and which is very interesting because we have lots and lots of regularities and surprises there. Let me just kind of explain a little bit these two stories. So we start with a finite abstract simplicial complex, can come from a graph, like here from the kite graph, and we have now two different things. We have an incidence story and we have an intersection story. For example, here this is visualized by looking at the graph where the individual sets are the vertices and you connect to if one is containing the other. So this is also called the barycentric refinement of this. But then we have also the connection story. This is often homotopic here most of the time, and we have here connect two simplices if they intersect. Now in the first case, when we are looking at the incidence, we have a calculus. We have an exterior derivative, which absolutely is the same than the exterior derivative we have in the continuum, just much easier, right? We have a map from k forms to k+1 forms, which is called the exterior derivative, the gradient, the divergence, or the curl in classical calculus. And then we can make this more elegant by putting everything together as this one matrix, and this Dirac matrix is d plus d star, which is the transpose d star, and then we have the square of it, which is the Hodge Laplacian, which has now here three blocks because we have a two-dimensional situation. Right? They are triangles here. They are not yet K4 subgraphs, not yet three-dimensional parts. So this is a two-dimensional story. So there are three blocks: the zeroth block, the first block, and the second block. And then you can look at the kernels of these matrices. These are the harmonic forms, and in this case, there is just one vector, 1, 1, 1, 1 vector, which is a harmonic. So there is just the Betti, the first Betti, the zeroth Betti number here is 1, the others are 0. These are invertible matrices. So we can read off cohomology from this, the Euler characteristic. We can write also in terms of these Betti numbers. This is Euler Poincaré, which is very easy to prove using the McKean-Singer result, which gives us a supersymmetry between the odd and even dimensional parts. The non-zero spectrum of these two blocks coincides with the spectrum of the odd dimensional blocks, which is here just one block. So there are lots of interesting things. I've just taught multivariable calculus. There's Stokes' theorem. Actually, in the discrete, it's almost a joke. You can write it down just immediately there. In the case when S is a surface, a manifold with boundary, this is the usual Stokes theorem. The integral of the derivative over the space is equal to the integral over the boundary of the field. So there are fields and there are geometries in this story. The fields are just the vectors, right? The Rn vectors. So these also exist here. We have also the same, we are working on the same Hilbert space, n-dimensional Hilbert space than here. So that's the thing. And then I was actually just wondering about the spectrum now this week a little bit, and so the spectral radius can be estimated quite easily by twice the degree. So D1, these are actually the diagonal entries. The maximal diagonal entry, you take the maximal diagonal, which is 4 here, twice 4, 2 times 4 is 8, and then this is actually kind of a total overkill. The first eigenvalue is actually just 4. This I cannot yet prove bounds for the individual eigenvalues like in the Kirchhoff Laplacian case. where I wrote this paper 2022, which gives us the upper bound for every eigenvalue, and I went into quivers in order to prove this. You might think that it also works by just doing induction with respect to edge reduction, but that doesn't work. And here I have a result about kind of an analog result, a boundary of the a bound for the eigenvalues of the connection Laplacian. So also that's something which I have used in the story of fusion. The fusion story was kind of a topological story. If you have a closed set, which is a subsimplicial complex, then you have a complement which is open, and you can look at the Betti numbers of the open set or Betti numbers of the closed set, and the sum of these is smaller or equal than the Betti number of G. That was using the spectral monotonicity, which can be refined a little bit, namely that the matrices, the actual Hodge matrices, like here also the connection matrices, they are principal submatrices if you take a subcomplex, which is very nice. So spectral monotonicity follows from this. It also implies more that the spectrum is interlaced, which is kind of cool. And so in this case, I was making some experiments, and I saw a three-dimensional sphere already, where this is, I mean, for k equal to 1, it's true, but where for larger k, smaller eigenvalues, it's wrong. So that these degrees here don't, form, at least not 2. It worked for 3 in that case, but maybe that also starts to fail at some point. So I don't yet know how to bound this. And this is a phenomena which is typically high-dimensional phenomena, that the degree of an edge, for example, degree of an edge can be larger than the degree of a higher dimensional space. Or like here it is true. Here what happens is, if a simplex intersects with another simplex, then also every larger simplex intersects. So here we can really kind of get immediately upper bound inductively. I will talk maybe more about this next week. But let me just say something more about the connection calculus, which is for me a really, really exciting thing. So this is something nature tells us, the right thing to do, to look at these connection matrices, because we don't have any singularities. If you look at the green function is traditionally always, related to the potential, like Newton's potential, 1 over r potential, comes from the green functions of the Laplacian in R3. So you can look at on any geometric space with an exterior derivative. You have also a natural green function, which is the inverse. So you want to solve the Poisson equation, right? So you have to invert the Laplacian, and you cannot do that in general, kind of in the classical framework. You cannot do that here, because we have always an eigenvalue 0. There's always an eigenvalue 0 here. Sometimes more if the space is more complex, especially in higher dimensions. Now, what happens here is there are some miracles. Namely, we can immediately write down the green function matrix, and unlike in this case where the inverse, even if you look at the pseudo-inverse, connects different parts of space which are very, very far away, which is nonsense from a relativistic point of view. This is also localized here. So the green function involves the open sets. So you take the Euler characteristic of the open intersections of the stars, and that gives you the green function entry. And that's localized too, because 2 points which are, these 2 simplices which are further away, they don't intersect, or if their open sets don't intersect, then you have a 0. So there is kind of some kind of causality in this framework, and it's also kind of nice to think about this as potential energy, because the sum over all potential energies, I have not that written down. Maybe I should write this down. The sum of the g x y. That's the Euler characteristic. Euler characteristic is somehow like an energy, total energy. So it's a very nice, so we have this, also we can read off the Euler characteristics, the number of positive eigenvalues minus the number of negative eigenvalues. Here from the spectrum alone, we cannot read off the Euler characteristic yet. I don't know how to do that. I don't think anybody knows how to do that, except if we know which eigenvalues belong to which form. Then of course you can do this because we can just look at the kernels. We can look at the 0 eigenvalues in each of these sectors. Right? The 0 sector, 1 sector, 2 sector. So in this case we can read off the Betti numbers. And so the Euler characteristic, in this case we can read it off just from this connection matrix. But this connection matrix here, kind of on the, this bosonic story, this connection matrix is not a block. This is not, this is irreducible actually. This is always an irreducible matrix, an irreducible 0-1 matrix if the space is connected. While here this is never irreducible, right? There are these blocks. This is reducible almost by definition. And so we have here kind of also a much nicer mathematics. We know how to deal with non-negative matrices. These are only 0-1. These are matrices which only have zeros and ones here in this case. And so we can estimate very easily the spectral radius. The spectral radius is smaller or equal than the sum here, the maximal, the number of entries here. That, if you add them up like here, this is 10. This is the maximal. This belongs to the triangle here. This triangle intersects with everything except this point 3. And this triangle intersects with everything except this point 2. So this is very connected here. This connection graph here is very dense. It's much higher dimension than that. Still, kind of, if you take a manifold, this is homotropic to that. So they are just closer connected with each other. They are nice. There's nicer mathematics involved. So you can look at the Shannon product, and so you behaves very nicely mathematically. Also, maybe just a remark, and that's kind of here because when you take this matrix, this is essentially an adjacency matrix of this graph here, except for the diagonal. But if you take powers of this matrix, then you just actually, you get a matrix which is non-zero, which is positive. You get a positive matrix. And if you have a positive matrix, then by Perron-Frobenius you have a unique maximal eigenvalue. And that's what we see here. This lambda 1 is usually much higher, like here. So this is almost 8 here, while the next one is 3. So this maximal eigenvalue is much bigger. The eigenvalue, it belongs then to the smallest the smallest eigenvalue of the green function, which is quite an interesting number, because this is kind of how large can you make perturbations to get away from the vacuum. Here the vacuum is stable, completely stable. You have a classical implicit function theorem works to continuous solutions because the matrices are invertible, while here you have a big mess. Right? The whole physics books, if you look at physics books, electromagnetism, everything, just the difficulty comes from the infinities which you have with the 1/r potential, for example. Here the potentials are all finite, everything is nice and beautiful. So yes, there's some interesting questions yet. I mean, one of the things which I don't know to get the natural upper bound here for the case eigenvalue. Similarly, then we have here it's much easier to do. If you take a maximal simplex a facet away, then you have a principal submatrix, and you can, immediately get this bound here. So there is still quite a bit of work to do on the spectral level. That's it for today.